días a todos y a todas. Mi reloj de mi computador no está sincronizado con mi reloj de pulsera, así que espero que sean las 12 o las 12:01 minuto. Disculpen la demora. Ya estamos admitiendo a todos nuestros colegas y compañeros, estudiantes, etcétera, de la sala de espera a la sala del día de hoy, 29 de junio. Bueno, este seminario, déjenme solamente colocar aquí mi ayuda de memoria. Como les decía, les doy la bienvenida. Recuerden que es un ciclo de seminarios que hemos organizado entre el CR2 y la Vicerrectoría de Investigación y Desarrollo de la Universidad de Chile, titulado Evaluación Económica de la Megasequía y otros impactos climáticos, la experiencia internacional. Y ha pasado muy rápido el tiempo. Esta ya es nuestra tercera y última sesión. Hemos tenido 3 seminarios previamente, en el cual hemos conocido de primera fuente las estrategias para evaluar los impactos frente a este tipo de fenómenos, sequías y otros eventos extremos, incluyendo aspectos metodológicos, alcances y limitaciones. En este nuevo encuentro contamos con la presencia del Dr. Thomas Corringham, quien nos realizará una presentación titulada Economic Impacts of Atmospheric Rivers in the Western United States. El Dr. Thomas Corringham es un economista e investigador del Instituto Scripps de Oceanography de la Universidad de California, San Diego. El doctor Thomas obtuvo su doctorado precisamente en economía en la Universidad de California, San Diego, y previamente tiene su formación en política y economía en la Universidad de Oxford, en el Reino Unido. Su trabajo se ha enfocado en entender los impactos económicos del cambio climático y eventos meteorológicos extremos. Sus áreas de especialización incluyen inundaciones catastróficas, incendios forestales, ríos atmosféricos, entre otros. Así que lo voy a darle de inmediato el pase a Tomás, pero antes de eso quería precisamente para contextualizar, si me dan un segundo, voy a compartir nuevamente mi pantalla. Quería contextualizar por qué vamos a hablar hoy día de ríos atmosféricos y eventualmente inundaciones en este ciclo de seminarios que originalmente estaba orientado a la megasequía. Y de hecho las primeras 2 presentaciones, recuerden que esta es la tercera, las primeras 2 presentaciones de José Medellín Azuara y después de Michael Hahnemann estuvieron en torno al tema de la evaluación de la megasequía. Pero sin embargo, incluso en un contexto en que las precipitaciones están siendo más deficitarias y van a continuar probablemente en ese mismo camino, es probable tener eventos extremos. Y muchas veces esos eventos extremos se pueden superponer en lo que le llamamos la megasequía, ¿cierto? Recuerden que originalmente pensábamos que era hasta el 2015, por lo menos sabemos que hasta el 2020, aún es temprano este invierno para saber qué va a pasar, pero al menos ya llevamos una década seca. Sin embargo, incluso en un contexto de megasequía podemos tener lo que le llamamos gigantes o estas grandes tormentas y producen un impacto muy importante, tanto en el medio ambiente como en la sociedad. Si bien es cierto, han ido desapareciendo y cada vez tenemos la percepción de que hay menos de ellos, eso es en Chile central, pero en la zona centro-sur de Chile continuamos con estos eventos muy extremos e incluso también acá en la zona central. Lo que hemos aprendido, y con esto termino, en los últimos años, nosotros estábamos acostumbrados a recibir grandes sistemas frontales fríos con una formación nubosa muy característica y muy amenazante. Y en los últimos años hemos aprendido que algunas veces las amenazas no parecen tan terribles inicialmente, como este caso que estoy mostrando en la pantalla, que se trata justamente de lo que denominamos un río atmosférico de características zonales, que además de tener precipitaciones muy copiosas, ocurren con temperaturas muy altas, y ese es el secreto perfecto para la combinación de precipitaciones altas y temperaturas también en general altas para un evento de precipitación, tener crecidas tan grandes como esta en el río Puelo con cerca de 4.000 metros cúbicos por segundo en determinado momento. Y por lo tanto, insisto, pese a que estamos en un contexto en que la sequía sigue avanzando y las condiciones deficitarias se han mantenido por más de una década, y esas también son las proyecciones a futuro, es muy importante siempre mantenernos alerta respecto a estos ríos atmosféricos zonales, a estas tormentas cálidas con sus impactos, y es precisamente de eso lo que vamos a aprender en la presentación de hoy, porque los ríos atmosféricos no son una característica únicamente de Chile, sino que ocurren en el resto del mundo, con particular énfasis en las costas oeste, como la de California y como la de Chile. Y por lo tanto, tengo el placer, como decía previamente, de presentar a Thomas Corringham, el doctor Thomas Corringham del Instituto Scripps de la Universidad de California, San Diego, y por lo tanto vamos a continuar de inmediato con su presentación. Thomas, thank you very much for for helping with all these seminars series. In fact, you made a contact with many of the panelists on the previous seminars, and we are so happy to having you this day. So the floor is all yours. Let me just stop sharing my screen. Thomas is fluent in Spanish, not that fluent, but he speaks Spanish. But for obvious reason, his presentation will be in English. So thank you so much again, Thomas, and we are now seeing your presentation perfectly.
Great, thank you, Renee. Thank you everyone for being here, and thanks so much for the invitation. Really excited to be able to present some of this work to you all. As Renee said, I speak a little Spanish, probably not enough to give the talk. My Spanish teacher, when she found out I was giving a talk in Chile, she said that I had to give the talk in Spanish, and I put the slides together at least.
You can speak Spanish at any time, maybe at the end or whatever, but we will give you a certificate for your teacher, for your professor in Spanish.
Great, thank you, Renee. What I'll be talking about today is and Renee, thank you for the great introduction. I'll be talking about the economic impacts of atmospheric rivers in the Western United States. And this is work that's done primarily through our center here at Scripps, the Center for Western Weather and Water Extremes, or CW3E. And below are a few of my colleagues that I just wanted to recognize. The outline of the talk, I'll be just discussing some features of atmospheric rivers to begin with, and then discussing the AR's category scale that was developed at Scripps. And the main part of my talk will be on atmospheric rivers and flood damages in the Western US, and also how we expect those damages to change with the changing climate. I got a little maybe overly enthusiastic yesterday in putting together slides. So I do have some slides on transportation costs associated with atmospheric rivers. And also, I know this is a seminar series on drought, so hopefully I'll have a little bit of time at the end to talk about forecast-informed reservoir operations, or FIRO. I took a crack at translating that, operaciones de embalse informadas por pronósticos meteorológicos. I'm not sure, maybe there's a better term for it, but hopefully I'll get to discuss that a little bit, because it kind of pertains to how our knowledge of atmospheric rivers can be used to mitigate some of the adverse impacts of drought. So a little bit about atmospheric rivers. They are these long, narrow bands of water vapor in the atmosphere, and they transport water from the tropics to the higher latitudes. They are typically thousands of kilometers long and a few hundred kilometers wide. And the average atmospheric river transports more moisture than twice the flow of the Amazon River at its outflow. The atmospheric rivers normally accompany cold fronts and extratropical cyclones, and they affect the west coasts of major land masses. I should say I kind of pulled all of these figures from Meteo Chile. They have a great discussion of atmospheric rivers on their website. The way that we typically measure the intensity of atmospheric rivers, and I'll be discussing this as we go through and relating it to damages, is through a quantity called integrated vapor transport. And by integrated, it means integrated over altitude. So it's all of the water vapor over a column of air at a specific location. And it's how fast that is moving through the air. So it's a combination of water vapor and also wind velocity. And it's measured in kilograms per meter per second. IVT of over 400 is considered to be fairly high, but we do sometimes observe IVT over 1200 kilograms per meter per second. So why do we care about atmospheric rivers in economic terms? Well, at least in the Western US, they form a large part of our water supply. So they are often instrumental in ending the droughts that we experience in the Southwest. What I'll be discussing is the other side of the equation, which is flood damages. And as the water vapor rises over mountainous topography, the water precipitates out as rain and snow, and that can sometimes cause significant flooding. I'll just discuss briefly the category scale that was developed by our director here at CW3E, Marty Ralph, and colleagues. This has been very useful in well, conducting analysis, but also in communicating the effects of atmospheric rivers to the public and within the scientific community. So I'll just explain this briefly. It's similar to the familiar hurricane scales, the Saffir-Simpson hurricane scale and the Fujita tornado scale, in that it ranges from 1 to 5. 1 is considered to be a weak atmospheric river, 5 is exceptional. And the way that the categories are determined is it's a combination of the intensity, and you can see on the right here, the y-axis is the intensity in IBT, and also the duration. So on the x-axis, how long the storm lasts. And you can kind of see a schematic on the left here. So it's arranged in increments of 250 kilograms per meter per second. So above 250 is a category 1 or AR1 storm. And then every increment of 250, it increases the ranking. And then it's adjusted by the duration of the storm. So if it's less than 1 day or 24 hours, then the storm is demoted 1 category. And if it's greater than 2 days, then we increase it. A couple of examples, I believe these are also from the Meteo Chile site. So one of the points that Marty Ralph and colleagues made in their paper describing the scale is that atmospheric rivers are not always damaging. The weaker atmospheric rivers are typically beneficial. So here's an example of an AR2 in Chile in June of 2017. There was intense precipitation over 3 days, but no damages really, and it served to partially alleviate the water deficit in the region. Here is an example of an extreme atmospheric river, and these are typically cause more damages than benefits. And this one led to the tragic landslides in Via Santa Lucia in December of 2017. Interestingly, the scale gives a general indication of the impacts, but there are exceptions. So 3 weeks after this devastating event in California, we saw the Montecito landslide mudflow event. Montecito is in Santa Barbara, which is just north of Los Angeles, and this happened in January of 2018. It was only an AR1 or 2, depending on how you look at it, but it was accompanied by what we call narrow cold frontal rain band. And this is an example where the antecedent conditions really matter. So this atmospheric river came on the heels of the Thomas Fire, which was a wildfire that affected Southern California. At the time, it was the biggest fire that we had seen in California. Since then, we've had much worse fire seasons in 2018 and 2020. But the fires stripped the steep slopes of their vegetation. And so when we had this extreme precipitation event, it led to these devastating mud flows and led to the loss of lives of 22 people and damages of over $250 million. So this is an example of a moderate AR that actually caused significant damage. More common in terms of damage are these extreme or exceptional ARs. So this was an AR4 when it passed over the Oroville Dam on the Feather River. It was actually an AR5 when it made landfall. And in this case, it led to the Oroville Dam Crisis. So Oroville is the tallest dam in California and holds the second greatest volume of all of our dam system. And this happened 7th of February, 2017, very active year for atmospheric rivers, led to the evacuation of 180,000 people, deployment of 23,000 National Guard members. And what actually happened was the emergency spillway was compromised. So they had to release the water through the emergency spillway, and it was kind of touch and go for a moment there. Turned out that there wasn't catastrophic flooding downriver, but the damage to the dam is ongoing, the repairs, and so far the costs are over $1 billion. And there's a nice paper here by Julie Vano and colleagues about the hydrologic and meteorologic conditions that led to this event. So it wasn't just the one AR, it was actually a series on top of very wet weather. The main paper I'm going to discuss today is one that we published in Science Advances in 2019, and it's a historical study of damages associated with flood damages associated with ARs in the Western US. So to set the stage, before we conducted this study, there had been studies of individual events. There was a theoretical study called ArcStorm. Here, the K indicates 1,000. So this was a simulation of a series of atmospheric rivers with a return period of 1 in 1,000 years. So pretty infrequent, pretty high intensity event. And this was in 2011. It was funded by the US Geological Survey. And they estimated the impacts of such a storm, were it to happen today, with the current infrastructure and current flood defenses, the cost they estimated would be $860 billion. So just to put that in context for California, the state product, the annual state product in California is about $3 trillion. So it would be almost coming up on a third of the state product. So it would have a very significant economic impact on the region and on the nation. A case could be made that the global financial markets are heavily focused on Silicon Valley as well, so there probably would be spillover effects into the global financial markets. There had also been a number of studies looking at specific events. So there was a 1995 event in Northern California that we'll discuss in a little bit more detail, and the damages were estimated at $5 billion, and a number of other events that were with damages estimated over $1 billion. But when we conducted the study, there had been no consistent studies of damages over time. So that's what we sought to provide. I think I probably provided enough motivation here, but this was the Great Flood of California of 1862. So another, you can see on the left a picture of Sacramento, the state capital, flooded. And this one, the estimated return period was 100 to 200 years. So this was 1862, so we're maybe due for another one. Well, come back to what preparations would be useful. The data sources that we used, we were lucky at finding data on impacts of natural disasters is difficult, as I'm sure any of you who work in the area know. We were able to find data on insured flood losses from the National Flood Insurance Program. So in the United States, there's really no private flood insurance market, but there is a federal flood insurance market. And it's a nice data set because it's very high temporal and spatial resolution. So it's daily losses, and we used community aggregated data, but you can actually get more finely resolved data. And we used 40 years of data. The one downside to using insured losses is that, at least in the United States, insurance is only provided for residential properties. So it misses the commercial properties, and it misses industrial and infrastructure damages. So we linked the flood insurance data to another damage data set, much lower resolution, to get kind of a scaling factor so that we could estimate the total impacts. On the atmospheric river data side, we used a catalog developed by Sasha Gershonov and colleagues that considered integrated vapor transport and at a 2.5 degree grid, so fairly coarse resolution, just over 100 kilometers. And they ran their reanalysis data through an AR detection algorithm. So we had a set of atmospheric rivers that were identified by their method and put together into a catalog. So we linked the atmospheric rivers by location to damage, and that's how we came up with our damage estimates. And we also made use of the AR scale developed by Ralph and colleagues in 2019. So some results here. This table shows some of the top events. 1995 turned out to be the highest damage in our record. Depending on how you look at it, I have a colleague who has rerun it with a different reanalysis product and found that 2005 actually had slightly higher damage, but his top 10 were the same as my top 10. So it seems fairly robust to the data. So what does an atmospheric river cost in the Western US? We found the average cost was about $28 million. So obviously that has pretty significant local impacts on whatever community it affects, but in terms of the broader economy, it's not that significant. And interestingly, the median damage was 0. So actually most of the atmospheric rivers that we observed didn't cause any insured losses. If you condition on those that actually did cause damage, obviously the median is twice that, but the median is about 2 million. So if you wanted to think of like what's a typical damaging atmospheric river, a couple $1 million in damages. So pretty low value. Again, could be very significant if it happens where you live. That said, the max damages were over $1 billion, and we saw those types of storms every 3 to 7 years. And interestingly, the damages associated with flooding, and I think this is true for most natural disasters, highly concentrated in a small number of events. Here we looked at the proportion of damages associated with flooding across the Western United States that were attributable to atmospheric rivers. And you can see here, the red dots indicate the fraction of damages associated with ARs. And we found that 84% of damages in the 11 Western states were caused by atmospheric rivers, or occurred at the same time as atmospheric rivers. And in some of the most highly affected regions on the coast, you can see over 99% of damages were AR related. We saw slightly lower proportions in Southern California and Arizona, but still quite significant. So I mentioned this event of January 1995. You can see in the top left, this is precipitable water. So classic atmospheric river pattern originating north of or west of Hawaii and extending to Northern California. We looked at a number of variables here. So IVT peaks on the 9th of January in the top panel there. Precipitation also over Sonoma County also peaks on the 9th. The stream flow actually peaks the next day, but it was already well above flood stage on the 9th. So the damages actually were, most of the damages were observed on the 8th, 9th, and 10th. And here's just a spatial picture of what the damages looked like. The blue area is the 100-year floodplain this is Sonoma County. So it's famous for wine growing. And it's just north of San Francisco. And this is the Russian River. So Russian River is an interesting river system, and Guerneville in particular, the town of Guerneville is an interesting town. It was built in the 1880s, so before people really understood the hydrology of the river. So there's a lot of property concentrated very close to the river within the flood zone. So it's a very high risk area. And we see repeated extreme flood events in Guerneville. There's been some effort by Sonoma County to raise a lot of the structures, to put them on stilts, to elevate the structures. So the damages are coming down over time, but it's still, still a very high risk community. Here are just I guess I'll draw your attention here to the map in the center. You can see these are the counties with the greatest damages over the last 40 years associated with atmospheric rivers. And by and large, it's the more populous counties. You can see Southern California, a bunch of the counties in the Pacific Northwest, but there are some other interesting ones like Sonoma, for example. Sacramento is there. And the one in Nevada, it's a large and long county. The damages were actually all concentrated in one town at the southern extent, Reno, Nevada, which is on the Truckee River, which flows from the Sierra Nevada mountain range. Here's a similar picture, and I think what's interesting here is if you look at the left, the greatest percentage of damages associated with ARs actually occurs in Northern California, the coastal regions. That's actually the epicenter of atmospheric river strength when you look at the historical record. But the population density is very low in that part of California. So on the right, you can actually see the absolute levels. And Los Angeles kind of stands out. And then obviously in Northern California, Sonoma because of the Russian River. And Sacramento, you can see just to the east. Looking at the scale, we decided to test the hypothesis that Ralph and colleagues had put forward, which was that the AR1 and 2 storms are mainly beneficial, but the AR4 and 5 are more dangerous. So what we did was we calculated the summary statistics by AR ranking. On the y-axis here, this is a logarithmic scale. So linear indicates an exponential increase. For weak atmospheric rivers, the median was about $100,000, so minimal damage. Moderate, it increased to about $400,000. By the time we reach strong AR category, the median is 3 million, extreme is 20 million, and then exceptional 260 million. So with each increase in category, we saw almost a 10-fold increase in median damages. I will mention, this is similar to the point I made about Montecito, there's large degree of variability. So if you look on the left, there were weak ARs that caused over $100 million in damage. Those are typically late in the season when soils were super saturated, occurring in areas with high populations. And there were exceptional ARs that caused very little in the way of damage, under $10 million. And those typically happened early in the season when the soils were able to absorb a lot of the moisture. And in areas where the population densities were very low. So for example, Northern California, Southern Oregon. Here on the left, it's not that easy to see, but in the top left column, you can see that the damages extend all the way into Arizona. And this is because there's a break in the mountain ranges between Baja Norte and Southern California across the transverse ranges, which allows the atmospheric rivers to penetrate inland. And in the bottom, well, in the middle bottom panel, you can kind of see there's a pattern where the damages extend inland along the Columbia River basin. So there is evidence of inland penetration for these atmospheric rivers. In the earlier picture, you saw there were very little damages in Nevada, with the exception of Reno. And this is because the Sierra Nevada range and then the White Mountains block the atmospheric rivers from moving inland. So topography is very important in determining what the damages are associated with these storms. On the right, the main point here is that typically, at least over the west, the damages occurred a day after landfall. This varies pretty significantly depending on where you are. Generally, when you're thinking about river flooding, there can be a significant lag between the precipitation event and the flooding downstream. This is what we observe on the eastern United States. In the west, the river systems are much shorter river systems. I presume this is the case in Chile as well. So we see the damages occur much closer to the time of landfall. There's a lag between the peak intensity of atmospheric rivers and the peak damages. So on the x-axis, you see the water year, which in the United States extends from October to September. And the blue is the peak atmospheric river intensity, and it occurs in November, December. Red is the top damages, which occurs in January. So that just indicates that the importance of antecedent soil moisture conditions. When the soils are already saturated, you see greater damage just because you see more runoff. I think I'll skip through this one, except just to say that we thought going into this that the orientation of the atmospheric river relative to the topography would be important. And you can see in Southern California, the mountain ranges are oriented from northwest to southeast, so kind of a diagonal orientation, whereas in the Pacific Northwest, the mountain ranges are much more north-south. And so we did find some evidence of the atmospheric rivers having a kind of southwest to northeast directionality, having greater impact in Southern California, and the west to east having more impact in the Pacific Northwest. But I think what was important was that the local topography is much more important. So you can see for Sonoma, for example, I showed this picture of the damages being concentrated along the lower reach of the Russian River. The basin itself is pretty wide, so you can have storms approaching from different directions, and the moisture will be captured and translated into runoff that affects the rivers downstream. Sacramento, local topography. This one, the blue area is not, the water content or the extent of water in normal conditions. It's the floodplain, and you can see the red dots is the urban area of Sacramento. So Sacramento is a very high risk area. We didn't see extreme damages in Sacramento over our 40-year record. I would say that's because we got lucky. If we saw something like the arc storm or a 200-year return period flood, I think Sacramento would be highly vulnerable. And there's a case to be made for investing significantly in improving and hardening the flood defenses in Sacramento. Los Angeles, just another example here. On the left, you can see along the coast there is Malibu, so very high value properties. And there the flooding is coastal. So the impact is much more wind speeds and wave heights than precipitation or stream flow. The kind of triangular shape is the Santa Monica Mountains. A lot of high value properties. On the south side, it's Beverly Hills and Hollywood. So there it's actually mud flows and debris flows that cause the damages. And in the lower right, this is Orange County, and it's a flat urban area that's subject to urban flooding. There's been a lot of work in the last 20 years to improve the flood defenses there. So I'm not sure if we would see that type of damage in the future. But this was just a nice picture I found on Meteo Chile, showing that the intensity of the atmospheric river varies by latitude. And at least in Chile, the strongest ones are to the south. I thought it was such a nice figure, I'd try to reproduce it for the Western US, and similar type of pattern, kind of reversed. So we see greater damages in the northern latitudes and lesser in the southern latitudes. The next work that I'd like to discuss is work that's currently under review that builds on this paper, looking at the effects of climate change, projecting future flood damages as a result of climate change. So these figures here are from a paper by Sasha Gershenov and colleagues. They used 16 different global climate models to forecast IVT and atmospheric rivers over the coming century. So it's synthetic data, extends back to 1950 through to 2100. This is a subset of the models that they used. And you can see a general increasing trend in max IVT per atmospheric river. And over the course of the century, fairly stable over the last 50 years, increasing. And then it's not obvious in this figure, but the greatest increase is end of century. I should mention this is the RCP 8.5 scenario, so it's business as usual. I guess we might say it's worst case. Perhaps if by some miracle we're able to reduce our emissions, we'll see lesser impacts. That kind of remains to be seen. The main result that was of interest to us that came out of this paper was the change in the distribution of precipitation that is projected by these models. So this is, again, the Russian River. And on the x-axis is the percentile of precipitation. And they found that over time, there will actually be a kind of decrease in precipitation in the middle of the distribution, but a significant increase in precipitation at the top end of the distribution. And why is that important? Well, I've showed this figure previously. The increase in damages associated with intensity doesn't scale linearly, it scales exponentially. So here, even this figure would be worrisome because we're going to be seeing, the prediction is we're going to be seeing more of these very intense events. But even more worrying because the damages tend to be concentrated in those intense events. We have the last 40 years of insured losses. And so we linked the characteristics of atmospheric rivers with the damages, mainly IVT, but also antecedent soil moisture and location. And these are our results. The time series here are damages rather than max IVT per AR, and you can see a steady increase. It's the same type of pattern. The dark blue is the ensemble mean over the 16 models. The black is the historical fitted values, so it approximates the fitted values quite well. And on the right, you see the distributions. So I guess the lowest one that's labeled 1.03, that's in the 1990s. That's the empirical distribution of modeled damages. The green is 2020s, so current. And so there's evidence that at least in terms of expected damages as modeled by the downscale global climate models, there's evidence that the expected damages have increased. I should say that if you look at the observational record, we don't see that. The observational record is fairly flat, and if you control for exposure, it actually goes down. And I would say the reason for that is we saw the extreme storms in the mid-90s, and particularly in 97 and 98 associated with the extreme El Nino event then. So when you actually look at the realizations of these time series, there's a lot of variability because of the natural variability in the climate cycle. What we're producing here are sort of expectations over a large number of models. And then in purple, you can see the distribution at the end of the century. And so the expected damages, annual expected damages rise from $1 billion a year to almost $3 billion. I'll just mention that Sasha and colleagues looked at all of the models and reduced it to just 5 that were most, that matched the historical data best. If we run just on those 5 models, the increase is from 1 to 3.5 billion, so it's slightly higher. These are the 16 different models. So you can see pretty consistent across the models. All of them show an increase over the duration of the time period. We also broke this down by AR rank. So this figure, I think, is interesting on the left. This shows the progression from 1950 to 2100. Again, this is all model data averaged over the 16 different models. And you can see that at the top, the blue and green are AR1 and AR2, and those aren't projected to change over the course of the century. What is projected to change is the 3 through 5, and it's a little difficult to see on this figure, but the The AR3 storms are expected to increase. So this is from Baja up to Seattle. The number is expected to increase from about 6 to 10, so almost a doubling. If you look at the AR4, it's expected to increase from 0.7 per year to 3.2 per year. So kind of a fourfold increase, 3 to 4-fold increase. And then the AR5s, the exceptional ARs in the historical record, they happen once in a decade. It's projected that by the end of the century, there will be 2 of these storms every 3 years. So the reasoning for this, if we believe the models, is that the warming temperatures will lead to more moisture in the atmosphere, and then the greater degree of moisture in the atmosphere leads to higher intensity. If you look across all of the different models and detection algorithms, the results are similar to those for hurricanes. There's a large amount of uncertainty over the frequency of these events. There's maybe some evidence that the frequency could decrease, but we do know that there's relative consistency in the models that of the storms that continue to occur, the intensity will increase. In terms of damages, you can see here that if you look kind of to the 1950s to 2000s, the historical record, the total damages, well, the total damages are in gray, but the damage is broken down by AR ranking are the colored lines here. And the yellow one is what accounted for most of the damages in the historical period. So these are AR3 storms. These are not the strongest storms, but there are more of them, so they account for more of the damage. By the end of century, it'll be AR4 and AR5 storms that account for most of the damages, according to these projections. A nice thing about these models is that we were able to build them at the county level. And so this gives us an indication of where we expect to see the biggest changes. There are a couple of obvious ways that you can look at changes in damages. So this is over a century. We also looked over the next 30 years, and I'll show a couple of results from that. But looking at the whole century of expected damages by county, on the left, we have the raw differences in numbers. So you can see, because there are certain counties where the baseline differences are quite high, typically the more populated and also the higher risk, like Sonoma and Sacramento. These are the ones where we expect to see the highest increase in damages per year. On the right, you see a ratio indicating what percent the damages will go up by. And Northern California and Southern Oregon light up. And partly that's just because the denominator is so low. Interestingly, the Sierra Nevadas light up as well. And there's a lot of water infrastructure on the Western Sierras. A lot of our dams and reservoirs are located there. So it kind of suggests the value of investing in hardening that infrastructure going forward. On the right, same data, just in tabular format, and I will draw your attention to the numbers on the right. The ratio, they were almost all positive across all of the counties we looked at. So uniform prediction of increased damages, and they range from 50% increase to 500% increase. Here, one of the feedback we got early in the project from our stakeholders was, okay, it's interesting to know what happens from 1990 to 2090, but we're more interested in what happens in the short term, so from 2020 to 2050. So we looked at that as well, and we found, if you wanted a rule of thumb, it's basically that we expect damages to increase by about 10% every decade. And those damages become, at least in the models, statistically significant by about the 2040s, 2050s. So I guess to summarize this work, we expect atmospheric rivers to become longer, wider, and wetter. This is from a paper by Espinosa and co-authors in 2018. As I've mentioned, modest increases in intensity could lead to significant increases in damages. And we expect, according to the projections, annual damages to increase from $1 to $3 billion. And an increase of 10% per decade until 2050. I will say that our record on which we built the models is only 40 years. So we don't really have any examples of these extreme events like the Great Flood of 1862 or like the Arc Storm. So these numbers, are not capturing these super extreme events. Another couple of caveats here. We assume we're basically just looking at the impact of the increased intensity of the storms. We don't look at changes in population, projected changes in population. So populations are expected to increase significantly over the rest of the century, so that could potentially increase damages. On the other hand, people are much smarter about where they build now, and there are policies in place to make sure that people don't build in floodplains. So, and also, as I mentioned, to raise properties that are in floodplains or move people out of high-risk areas. So those policies could actually reduce damages. The other major factor we haven't considered that we're looking at in current studies is the joint impact of sea level rise and increased intensity of these storms. So as the sea level rises, we would expect to see more coastal flooding. The work speaks to the need to improve predictions of atmospheric rivers. If you have better predictions, you can potentially evacuate people from areas ahead of the storms to reduce damages. And the long-range forecasts in the maps that I showed could be used to direct resources to the areas that are going to see the greatest increase in risk. I will just mention there's another nice paper that just came out this year by Alan Rhodes and co-authors at Berkeley. They considered, they only used one global climate model, but they considered, whereas we just looked at RCP 8.5, they looked at a range of scenarios. And the figure here on the right, you can see at the +3 degrees increase in temperature by end of century, very similar to our results, an increase from 1 billion to just over 3 billion. If we're able to, as a society, as a global society, reduce our emissions or pull carbon from the atmosphere, we could potentially reduce those impacts. So I wasn't sure how much I'd be able to cover. So I'm going to skip the next slide because it's I do have more that I can talk about. I think this will perhaps bring us to the end of the presentation. Because the series is about drought, I wanted to relate some of the research that we do at CW3E to the question of drought. Obviously, in California, as in Chile, it's a significant problem. So we had a significant drought over the early 2010s, which Josue talked about. I think Michael Hanneman also discussed that drought. And we're in drought conditions again. The governor of California just last month declared officially that it's a drought, which basically means that we're in the second year of drought. And conditions are drier than we've seen them in a very long time across most of California, which has impacts for wildfire season, has impacts for agriculture, obviously. So one of the programs that we work on in the center is forecast-informed reservoir operations. And if you look at the lower right, I'll just talk you through this. I have other slides that are later in the presentation, and those will be posted. So if you're interested in more detail, you can certainly look at those. The idea here in the lower right, on the x-axis is the water year, so from October through September. And on the y-axis is the volume of water in this case in Lake Mendocino, which is also the Russian River Basin, just upstream of Kernville. And the curves here indicate the allowable amount of water that the reservoir operator can have in the reservoir. So so the actual capacity of this particular reservoir is about 120,000 acre feet. But what's allowed in the summer is 100,000. So you have to obviously keep the reservoir below a certain level. There's a trade-off in reservoir management. The main objective is to stop flooding, and then the secondary objective is to increase the water supply or to save water for the dry season. So in the dry season, from May through October, the amount of water that can be stored is quite high. And then in the wet season, the flood pool is much lower. So it's reduced to 70,000. And the idea behind forecast-informed reservoir operations is that if you have sufficiently good forecasts of incoming storms, then you could release water ahead of the storm. And the advantage to that is that you're able to limit the flood risk while also increasing the safe amount of water that you can keep in the winter. So the blue area is CW3E ran a number of simulations, hundreds of thousands of simulations of storm events and our prediction capabilities and how well the reservoir would be able to release the water, and found that we were able to keep the flood risk constant, so not increase the flood risk, but allow for the winter pool to be increased. And in this particular example, on the lower right, the program has been in operation for 5 years, and in 2019, 2020, we actually implemented our proposed changes to the rule curve, which is this curve here. And the black curve is what actually happened. The orange curve is what we simulated would have happened without the change in policy. So we were actually able to achieve a 20% increase in storage at this particular reservoir. So when you consider the alternatives to this program, maybe I can cycle through here to some of the California. The alternatives are you could build new dams, which is politically very difficult. You could increase the height of existing dams, which is very expensive. You can build a new transport infrastructure. So on the right, this is a proposed tunnel that transports water from Northern California to Southern California to the State Water Project through the Bay Delta. This is called the California Water Fix. Some of the other solutions that are on the table, the Sustainable Groundwater Management Act has been passed, so that should alleviate some of the problems. I think Josue discussed Sigma. FloodMAR, which is flood managed aquifer recharge. The idea there is when you have flooding, rather than let all of the water flow out through the river systems to the sea, you divert some of the water to agricultural lands and it seeps back into the aquifers to recharge the water supply. Conservation, obviously, if you can convince people to use less water, and then recycling water. There's green infrastructure that can be developed, as well as the gray infrastructure, so restoring floodplains. And then there are new technologies that could be employed. But I'll just mention this. This is the water fix. This is the tunnel that's meant to flow, transport water from Northern California to Southern California. It's politically very contentious. So on the left, you can see Los Angeles Economic Development Council saying, supporting the California water fix. On the right, you can see the Sierra Club, which is an environmental organization in California, saying that they don't approve of it. This was actually a few years ago. The plan has changed somewhat, so things have changed a little on the ground. Here's perhaps the picture I should have shown you when describing FIRO. The big spike there is an atmospheric river, and the question was, under previous management regime, you would have to release all of that water, and so you would lose it. So by pre-releasing some of it, you can keep the rest of it. Here again is the final result from our application of the new program. And from an economic standpoint, this doesn't require raising the dam. It doesn't require building a new dam. All it requires is high enough quality forecasts. And that is something that we've managed to develop over the last 20 years. We have good enough forecasts today that we can actually implement this. So CW3E, this was a small reservoir on a small river basin. We are now trying to transfer the technology to Oroville and New Buller's Bar, which are much larger reservoirs in the Sierras. And we also have had a pilot project in Southern California, Lake Prado, that feeds that provides water to all of Orange County. So we have a number of projects in the works to see how well this transfers to other reservoirs. I have a bunch of slides here that are very interesting, where we actually look at the economic benefits. So for FIRO in Lake Mendocino, I mentioned that we saw an average of, well, in this particular year, a 20% increase. When you run all of the simulations, it's somewhere from 15 to 30%. If you run the numbers and find out what the economic value is, this amount, but it's a small reservoir. Compared to the actual costs of implementing this, the program costs of FIRO for the last 5 years have been on the order of 5 million. So within a year, it pays for itself. And then the costs of actually running FIRO over time are fairly low. You just have to change the decision support tool and ensure that the forecasts are high enough quality, which we believe they are. At this point, I will end my talk. And so, yes, thank you for your attention. The website for CW3E is there, and my email is at the top here. So I know the center is very interested in working in other areas that are impacted by atmospheric rivers, like Chile. Personally, I'm very interested in doing similar work around the world. So if you are interested in this work, and especially if you know of useful data sources, then that's something that I'd be very interested in talking with you about. So there's my contact information, and I'm happy to take some questions. Thank you.
That's great, Tom. Thank you so much for the presentation. It was very illuminating. And thank you for the effort of putting all these slides in Spanish. So we fully appreciate that effort. That went very well. Thanks a lot.
It was a lot
Tom.
of fun, Renee.
Tom, we have like 10 minutes, I will say. And speaking of, so I will jump immediately to one of the questions that I have here is, I was fascinated with all your maps. You cover several things, but you start looking the impact of some past event, right? Event in the recent past, ARs in the recent past.
Yeah.
And you have all these really nice maps with the different impacts in different regions. So what is the database that you use? Because we have the same thing for the ARs. We can classify them, and we know when they occur, etc. But which data set you use in the Western United States to construct these maps of this estimated cost? At some moment I read their insurance losses, but I'm not sure how you proceed with that.
So yeah, in the United States, since the 60s, there's been a program called the National Flood Insurance Program, and it's a federally backed set of insurance policies. So if you are a homeowner and you live in the 100-year floodplain, then you can buy flood insurance. You can actually buy flood insurance if you live out of the floodplain. And so since 1978, the program has kept electronic records. So they do have, they actually have address level damages by day. They don't provide the address level, but slightly aggregated. So you know, it's a fairly high spatial resolution where the damages occurred. As I said, the downside is that it only captures a small amount of the losses. So we scale it up by other data sets that capture total losses. There's a database in the US called SHELDIS, which is run by Arizona State University. They bring in a lot of different sources, including news reports and the flood insurance data. And they are able to provide data at the county monthly level, which is not quite high enough resolution to look at individual meteorological events, but by linking it to the flood insurance, we're able to get estimates of damages. One other thing I would say, like if you don't have access to insurance data, then I think the next best thing is looking at news reports. That's more time consuming. Probably the best thing would be to actually go to the local administrative units and see if they have damage estimates, but that's very time consuming. It would take a fair amount of research effort.
Here, yeah, no, well, this emphasizes, of course, the importance of having these data sets or databases. And here I will say that we have some of them. So yeah, but maybe you can take some regions as a case study, and then, as you said, to scale to the rest of the country or part of the country. So, okay, that's that. But it's very impressive, these results, but it's because the analysis that you did, but also because you have this wonderful data set. Incredible. So thank you so much.
I will just add, Renee, like it is possible to do simulations as well, that we have increasingly good models of damage as a function of stream flow. They're very computationally expensive though. So doing the statistical approach that we did is simpler from a computational standpoint.
Oh yeah, that's a good alternative. Maybe we will have to use a mix of, as you said, modeling and direct observations and go. We said that we do a little bit of archaeology and looking the records in the newspapers, but that can be done. And we have a system that is fairly well organized. They keep data and records of the damage, not necessarily in economic units like dollars or Chilean pesos, whatever, but they know how many houses were affected, etc. So this can be done at least partially. Felipe, I don't know if you're there. Oh, you tell me that there is a...
Yeah, I'm here. There are three questions
Go ahead,
in the
Felipe.
chat. So no, I want to tell you one question. I sort of complement that. One of the questions is the following. They say, for estimating costs, you need an insurance market, mandatory by regulation. Is this the case? That's the question. And I want you to sort of explain us a little more about the cost that you estimated. What are the main sources of that cost? How do you evaluate that? And what are the policies that you have available to sort of go with these issues?
Sure. So in terms of the insurance, it's pretty far from like a perfect economic market. There are all kinds of inefficiencies and kind of perverse incentives associated with the National Flood Insurance Program. The flood maps aren't that great. In terms of the mandatory regulations, technically, if you have a mortgage, a federally backed mortgage in the United States, and you live within the 100-year floodplain, you are required to have flood insurance. The issue that we've seen in the past, and this may be changing, but in the past, people would sign up for the insurance for the first year and then drop it. I mean, as anyone who is in the economics field here would know, people are very bad at judging very low probability events and the impacts of low probability events. So yeah, there are difficulties there. In terms of parsing out like what damages are associated with which factors, I think that would be very interesting, getting a better sense of when you look at the total damages that we estimated from in this particular case, a National Weather Service data set that covered 83 to 2003 that we used to link, or from the Sheldis data. To my knowledge, it's not broken down by type of damage. So we don't know if it's residential, commercial, industrial, or infrastructure, but that would be very useful if we could put that together.
Those are the, sorry, Don, but those are the only sources of damage.
Data. And then there is one other source of data that is quite useful, which is there are small business administration loans. So after an event, you can get a subsidized loan to rebuild. With the disaster assistance, with the flood insurance, and with the subsidized loans, there's an equity issue here, which is that we found that it's the higher socioeconomic neighborhoods that tend to get that money, whereas the more vulnerable communities are less likely to get the money. So there's a kind of bias in reporting, which needs to be considered, and it's kind of an active area of research there.
Yeah, no, again, we have something called ONEMI, which is similar to FEMA, I suppose, and these are the guys that are in charge of keeping records of the damage. Because somebody was commenting there that, of course, if you have an insurance market, you can take a look of that, and that will provide at least a line to construct. But here, as you can imagine, there is vast sector of the society that are not under any insurance. But yeah, we definitely want to advance a little bit on that. There is a few more questions. Dennis Boskurt, a colleague of us here at the center that's currently working in Valparaiso. Dennis, I don't know if you want to formulate your question directly. I don't know if you're there.
Yeah, Rene.
Hi, Dennis.
My camera, sorry for that. So my question is the one of the plot that Tom showed about the interquartile range of economical cost prediction. So I wonder whether this interquartile range mostly determined by the physical structures of the R, or some extra outlier introduced by the economical cost detection. I wonder which more impact on this interquartile range? Thank you.
That's a great question. I think, and it's actually one that the reviewers asked on the paper, how much of the uncertainty is due to model uncertainty, how much of it is detection algorithm for the atmospheric rivers, and how much of it is economic model. We do have uncertainty estimates on the economic model because we understand that model. The detection algorithms is somewhat quantified in the literature. In an ideal world, we would be able to run through a bunch of different detection algorithms in addition to the models. So I suppose my short answer here is we don't have a good sense of that yet, but it is something that we're looking into.
Good. And there is one more question. By the way, I also found fascinating that you described briefly, but this is also very illuminating this FIRO, these ideas that's because especially in times of drought, you cannot lose any water. So if there is a chance of making a better decision in this dam administration and how you operate them, that's a great idea. And I know that in September you have one of these FIRO symposium or something like that. So I don't know exactly.
Yes, I should mention that we do have every year we have a symposium about the forecast informed reservoir operations, and I think this year the plan is actually to make it in person again. I don't know if that will happen, obviously, given the pandemic, but it will be possible to attend remotely. So I think if you contact me or Renee, I'm sure we'll have the information if you're interested in attending.
I was talking with Marty about that. And speaking of that, there is one more question from Miguel Lagos. Miguel, who is a hydrologist. I don't know if Miguel, are you there?
Yes. Thank you, Tom, for the presentation. My question is, how much does it cost to bring at the same table meteorologist, hydrologist, and economicist? Because here in Chile, we have still a very fragmented point of view regarding this thing. So do we need a center? Do we need a project? Politicians? What is your experience?
How long did it take this process?
Right. So at the Atmospheric River Conference, the first one I went to that was at Scripps, I was just chatting with someone over drinks, and they said, "I'm amazed at how interdisciplinary this conference is. There are meteorologists and hydrologists." And as an economist, I was sort of standing there saying, "Yeah, I guess I feel like a fish out of water here." So yes, it's difficult to bring everyone together. And as you probably know, there are a lot of incentives in academia for keeping people in their silos. So we're trying to break those down. I think a center that looks at the economic impacts of extreme events would be great. There are a few places that exist like that around the world. It would be great if we could build one like that at UCSD or Scripps. So yeah, it's a process. At least on the projects that I've been working on through CW3E, we typically work with academics. We usually will have a roundtable early on in the project development phase where we will invite economists. The connection with policy is much stronger for both we have an AR recon program where we do monitoring on InSight with aircraft, and then we have the FIRO program. These are our big programs, and for both of those, we're very connected with the policy community. With economics, we typically bring in outside experts, often from consulting firms, but also academics, and they will come in early in the process, but it's still not fully integrated. So that's something we're working on. So yeah, I would say it's a difficult question, but certainly, I mean, I'm an economist, so I'm biased. I think it's crucial that we do that.
No, this is precisely the objective of these kind of seminars. And again, we thank so much, Tom and Miguel. We are trying to advance on this. And I think that's looking in extremes, both in extreme dryness, like the mega drought, but also in these extreme events with a lot of rainfall or precipitation. It's very important because these are at the end, as one of the Tom figures show, you can have in average that the ARs maybe will not change, but only if this small AR5, or I mean this infrequent AR5 that are the more damaging, they increase by 1 or 2%. These are the ones that will produce a lot of damage. So we definitely want to look them in details. There is also, Tom also showed, I think that another idea that is revolving around here is this idea of the compound events, because as Tom said, sometimes you don't need, we were surprised this year, for instance, we have an AR that I will classify in terms of the IVT as an AR3, but because it came in the wrong season and with high temperatures, the effects were very, very intense here in central Chile in January. So we had to build around these events and continue and learning of this international experience. And this has been precisely the objective of this series of seminars. So once again, I want to, quiero agradecer a Tom. Fue muy buena tu presentación, Tom, muy ilustrativa y nuevamente muchas gracias por darte el trabajo de traducir todas esas slides al español o al castellano. Aprendimos mucho, al igual que en todas las otras seminarios. Todos los seminarios están en nuestra página web del CR2, en los videos. Yo le pregunté a Tom, y creo que estás de acuerdo, si podemos colocar tu video ahí también, Tom, porque bueno, hay gente que lo ve después y todo eso. Así que no sé, Felipe, o si alguien más quisiera hacer algún comentario.
I'm fine.
Bien, bueno, también queremos ser respetuosos del tiempo de Tom y de todos los colegas. Aprovecho de saludar ahí a Patricio Bernal. No sabía que Patricio Bernal era, pero ahora que veo es un colega nuestro que está aquí en Chile, pero también trabaja con los colegas australianos. Así que un gusto verlo a todos. Agradezco también a Susana, a Rocío, a Michelle por todo el apoyo logístico para esta serie de conferencias. Y bueno, vamos a seguir trabajando en esto. Así que muchas gracias y nuevamente muchas gracias, Tom.
Gracias, René. Gracias,
un gran
Felipe.
saludo para ti y para todos para toda la audiencia.
Muchas gracias a todos.
Que tengan una buena jornada en el día de hoy y en el resto de la semana. Muchas gracias.